do one more example of a partial differential equation. In all the previous three examples, the ordinary differential equations we had to solve turned out to be first order. This one, we're gonna get a second order equation. That's about the only thing that's really different here. So here's our equation where this k is greater than 0. So this means second partial with respect to x, so that will be x. Excuse me, I was one chart ahead. Here's the equation we're going to solve. That's the same. So if I rewrite it with the other notation, this would be u sub xx. This is u sub t, where u equals product of big X, big T. Before we had x and y. It doesn't matter what the variables are. But if it's a function of little t, we call the function big T. In product notation, say use a function, this product xt, which means u sub double x is x double prime t. U sub t is xt prime. Going from here to there is painless for you now. Do some algebra, I'll divide by kxt. There might have been another way to separate it, but I did this for convenience. So when I do that, let's see. These big T's cancels and these K's cancel. On the right side, the X's cancel. So I'm left with this. At this point, they're separated. All X stuff on the left, all T stuff on the right. Set them equal to the same constant. That gives me two ordinary differential equations. X double prime plus lambda x equals 0, one of them, and t prime plus or minus, plus lambda kt. And here's why I divided through by k. I wanted this x equation to look like a standard second order equation that we have on our formula sheet. Both these equations are in a form that are on already pre-solved ordinary differential equations that we have listed on a formula sheet. I talked about the formula sheet some recordings ago. We have a whole list of pre-solved ordinary differential equations and their general solutions. This T equation is the first order equation that showed up, I believe, in all three previous examples, or at least two of them, I believe. So the T solution is this: some arbitrary constant times e to the minus k lambda little t. This x guy is the second order ordinary differential equation. And its solution is going to depend on lambda. Go back to the formula sheet for this kind of guy. It depends on whether lambda is positive, negative, or exactly 0. You get three different cases. You got to go through those two different cases. If lambda is negative, we'll call it minus some alpha squared, which gives us this solution. And I'm using, remember in this case, I could have used one of two formats. I'm going to use the hyperbolic trig format because that's what we're going to be using most of the next several recordings or several modules in this course. And we have to use the same lambda for both solutions. So the T solution has to use the same lambda as the X solution. So when I use minus alpha squared for lambda, that means T is this. More lambda there, it's alpha squared stuff. So the total solution is the product of those two guys. This solution and this solution. I can at least combine some of the arbitrary constants. I still have two of them, C sub 1 and C sub 2, I'll call it. So this is one possible solution to the equation. Lambda could also equal 0, in which case here's the x's general solution. T solution when lambda equals 0, remember the T solution was 0. So if lambda is 0, this is just 1. T is just a constant. And again, total solution is the product of the two. So it is this. No more needs to be said there. And finally, if lambda is positive, we call it alpha squared. That gives us this solution for the x. Off our formula sheet. T solution must use the same lambda. Both equations got to use the same, must use the same lambda. Total solution is the product of the two solutions, x and the t. Some of the constants can be absorbed. I'm still left with two constants in that solution. So I have three possible different solutions. And if this is the whole equation, the whole problem, no boundary conditions, you just have to list all three solutions. So all these examples so far had no boundary conditions on them. Next thing we're going to do is put boundary conditions on these guys. And then we start having some fun.